Hello friends, I invite you to the lecture 25 Process Capability Analysis Measures and Indices, and I would like to remind you that we are in the measure phase of our DMAIC Six Sigma journey, and last time we have talked about various concepts, key concepts related to process capability analysis. This time we will go deeper and try to appreciate the importance of various measures and indices. So, once again I would like to emphasize that a bad system will beat a good person every time, and it is necessary to see that my processes are really capable enough to meet the customer expectations or not. So, processes which are not meeting the customer expectations, specifications, then this processes first needs to be corrected, and once you achieve the desired capability of the process, then only you can really produce the good quality products. So, if we just see the small recap, then we talked about need of process capability analysis, natural process limits, specification limit, control limits, natural tolerance limits, short term and long term process capability, differences between process performance metrics and process capability indices. So many a times you get confused. We had seen DPMO, DPU, how to find sigma level, all these are process performance metrics. When we talk about process capability indices, these are the aggregate measures, basically represents the capability of the process, and CP, CPM, CPK, these are the various measures that we will see in this particular lecture. So we would also keep revising couple of things which we discussed last time, but in addition to that we will mainly focus on process capability and capability indices in this lecture, process performance and performance indices, short term, long term capabilities and related indices, capability related assumptions, then conducting process capability study, natural process limit, specification limit, and process performance metrics. So these are the broad topics that we would like to see, and simultaneously I would like to give you some recap of the last lecture so that you can strengthen your understanding on process capability indices. So we have seen what is process capability. So typically it expresses the capability of the process to meet customer specifications, and to what extent my process is capable enough to meet the customer requirement. So typically it is expressed as Six Sigma, and where sigma is the sample standard deviation of the process which is under a state of control. So please be reminded that I can only conduct the process capability study if my process is under the state of statistical control. We have various process capability indices, but basically these are aggregate measures, and they typically say check the goodness of the process performance and ability to meet the specifications. So indices incorporate locations as well as variability both, and we will try to see it through different indices. So broadly I can classify the indices as short term indice, long term indice, CP, CPK, CPM, CPU, CPL. These are the various short term indices, and long term indices PP, PPK, PPM. So when I say short term, I am specific on a particular subgroup or a limited period of time and trying to capture the status of process. When I say long term, then for the entire horizon, overall say working period, long span, I am trying to observe the process, and then I am trying to say calculate the process capability to comment about the process performance. So basically it is a dimensionless number and is used to represent the ability to meet customer specification limit, and typically for short term, as we have seen, CP, CPK and CPM are the widely used process capability indices. So just see the expression for CP. I am considering the overall band USL minus LSL divided by 6 sigma, that is the variability associated. So when I say USL minus LSL by 6 sigma, typically it tries to capture the voice of the customer and voice of the process. So VOC divided by voice of process, VOP, tolerances divided by natural process variation. So we have certain guidelines that CP values greater than equal to 1 indicates the process is technically capable. When I say CP is equal to 2, then it represents the world class performance like 6 sigma performance, and CP value equal to 2 is said to represent typically your 6 sigma performance which we are aiming for, and CP index is limited to use since it does not address the center of a process. So process has a center, mean as well as the variability, but typically CP does not take into account the center or shift in the mean, because over a period of time there may be change in the setting and process may get shifted to the new mean. This part is not considered, and that is why the new measure is developed, that is CPK. So CPK is basically minimum of USL minus X bar divided by, so X bar is your process average, USL is upper specification limit, divided by 3 sigma, and another term that we calculate is X bar minus LSL divided by 3 sigma. So I will take minimum of these two to check whether my process also meets the center requirement or not, or it is now performing poorly because there is shift in say center or mean value. So typically CPK determines the process proximity of the process average to the nearest specification, either lower or upper, and we can note that one specification limit must be stated in order to compute the CPK. Sometimes some products they have only one specification limit, so it's okay, but at least you should have one specification limit. So CPK can be easily converted to a sigma level using sigma level is equal to 3 into CPK, and when the process average is obtained from control chart, X bar is typically replaced by X double bar. So let us see the example to make the idea clear. Suppose you have a batch process typically produces high lactose syrup with a specification on the dextrose equivalent, that is to 6 to 6.15, and the D's are normally distributed. So I assume that my production is normally distributed and a control chart shows the process is stable. So the first requirement for going for process capability is satisfied. The standard deviation of the process is 0.035 and the D is from the random sample of 30. Batches have a sample mean of 6.05. Now I want to comment on the capability of this process. So let me find CP and CPK. So these two measures, they do not have any conflict with each other. In fact, they provide the more information complementary to each other, and I would like to find both CP and CPK. So here my CP is tolerance divided by 6 sigma. You say it is voice of customer divided by voice of process, or sometimes you say USL minus LSL divided by 6 sigma. So here it comes out to be 0.71. So this is the value I am referring. This is 0.71. Now you can see that CP is less than 1. So when the CP is less than 1, my say threshold limit says that if it is equal to 1 or more than 1, technically my process is capable enough, but here my process is not capable. Now if I investigate further and find out the CPK, then I will take the minimum of these two with respect to say upper and lower specification limit compared with the mean value, and I will get 0.48. So, CPK 0.48 typically indicates that process is even less capable relative to the lower specification limit. So, number one conclusion, process is not capable, and second, process is even very much less capable compared to relative to the lower specification limit. So, you have other measures like PP, PPK, PPM. So, you would be wondering what is the difference. I have already highlighted that when I say CP, CPK, CPM, typically this particular measures they go by the subgroup standard deviation within standard deviation, and when I go by PP, PPM, this is more pertaining to the long term process capability, and it goes with say variability of all the data or the process which is being observed for a long period of time, and this is where CP, CPK, CPM are short term measures to investigate the process, and PP, PPM, PPK are long term measures for investigating the capability of the process. So, you have CP and PP, this do not take into account the shift in mean or location of the process. You have CPK, CPU, CPL, PPK, PPU, PPL, short term and long term respectively. They do consider the center as well as location of the process, and if my process because of say usage, wear and tear of some of the components or problem in the setting has shifted to the other mean, then that would be captured by this CPK, PPK, CPU, CPL measures. CP is basically measures the process potential. So, please try to focus on this particular word, that CP measures the process potential. So, what the process capability could be if there were no drifts in the process location, there is no shift disturbance in the setting. In that case, what is the capability of my process, what is the potential of my process. When you say CPK, typically it talks about the measure of the process performance. So, even if there is a shift, there is a change in setting, shift in the mean, to what extent my process would be capable enough to produce the products which can meet the customer specification. When I talk about it, it is about process performance. And you can see the third one, that is CPM. So, this is typically called Taguchi Capability Index, and here instead of I would say some center value or mean value, I will talk about the target value. So, there is a target value which I am trying to hit as much as possible, and to what extent my process is capable enough to meet this target value. When my interest of analysis is this, then I would make use of CPM, that is Taguchi Capability Index. So, CP is USL minus LSL by 6 sigma, desirable is greater than or equal to 1. CP, when you talk about long term, you have to consider, you talk about the short term, you have to consider the short term process spread sigma 6 sigma ST. When you talk about the long term, you will consider the long term process spread 6 sigma LT. You are allowing the process, observing the process for a longer or extended period of time, and then computing the standard deviation. So, just see this and you will get an idea that here CP is greater than 1, and now you can relate this with the understanding we evolved in the previous class. So, that time we just commented about the health of the process, capability of the process in terms of upper and lower specification limit and tolerance limit, natural tolerance limit. Here we are also relating that with the CP value. So, to remind you, tolerance limits basically decided by the process variability, capability of the process, and specification limits are given by the customer. So, this is a process which is capable, and we can very well see that my upper natural tolerance limit and lower natural tolerance limit, they are well within the upper and lower specification limit. So, my process is capable enough to meet or produce the products as per the specifications. So, this is my design width. I have to design my product process within this particular range, and this is typically my process Z. I call it Z because we are referring to the normal distribution. So, you can find process Z as USL minus LSL divided by 2 sigma. So, it is the number of standard deviation in half of the design width, and you can find out ZST, it is short term. So, USL minus LSL divided by 2 sigma ST short term, and CP is equal to ZST divided by 3. It is a standard expression because half of the width I am considering. So, in a 6 sigma process, obviously my ZST ST would be 6. So, process with specification limit at 6 sigma, you can see here that my particular process has plus 6 sigma, minus 6 sigma, and the number of components I would be producing which is defective is only 0.001 ppm on either side. And again I would say that 6 sigma means not larger, 6 sigma means a process which has extremely less variability, and hence it can give you the 6 sigma outcome, that is 3.4 say defectives per million, or here you can say 0.001 parts per million. So, just see to remind you, and as I mentioned that 6 sigma, this is my nominal value, this is my 6 sigma, and this is my 6 sigma curve. So, I have extremely less variability. This is my upper specification, this is my lower specification, and you can see that this process, because it is part of say well within the upper and lower, the probability that I would produce the defective part is very less. As you move to 4 sigma, then your quality level goes down, 2 sigma it further goes down, and so on. So, this is what we have seen. I would like to remind you again that if my process is controlled within plus or minus 1 sigma, then expected frequency outside range 1 in 3, very high, 1 in 3. If you see 2 sigma, 1 in 22, if you see 3 sigma, 1 in 370, and if you see 4 sigma, 1 in 15,787, if you see 5 sigma, 1 in say 17,44,278, and if you see 6 sigma, then the probability of producing defective component is very less. You can once again see that when I talk about the process capability, this is my process which is centered at mean. This is my process which is centered at mean, and you can see that there could be a shift of 1.5 sigma this side, there could be a shift of 1.5 sigma this side, and even if there is a 1.5 sigma shift, I would only be producing 3.4 ppm on the either side. So, this is where I am trying to achieve the reduction in the process variability, but in order to do so, first I must have an idea what is the capability of my process and what are the measures necessary to improve the capability. So, there is a couple of examples I am including to help you to appreciate the concept in detail. So, let us say specification of the inside diameter of casing for water meter are 90 plus or minus 4 mm, and a random sample of 10 meters gave the following observations. So, there is 87, 89, so diameter is measured in mm, 87, 91 and so on. We are expected to compute the CP index and comment, assuming the distribution is normal, and suppose the monthly production rate of such water meter is 4 million units. For any product outside the specification limit, the cost of scrapping this particular meter, water meter, is let us say $2.5. Estimate the monthly scrap cost, and what measures would you like to recommend to improve the condition. So, this is just the computation which can be easily followed. So, I have the x bar, I have taken the x square, I can find out the x bar. So, this is the total, 890 divided by 10 is 89. I can find the sample variance. So, I have 79234, then this is the value 890 whole square divided by 10 and divided by 9. So, my S square is 2.667. I can find the standard deviation S as the square root, and CP comes out to be 0.816. So, I would obviously say CP is less than 1, so it is not desirable and my process is actually not capable. So, now the issue is that if it is not capable, then how much amount of scrap I would be producing, non-conforming items I would be producing. So, here you can see that you have 86 and 94, because 90 plus or minus, if you just see the specifications, then it is this is 90 plus or minus 4 mm. So, 86 to 94 is the specification range, and if I consider this, then this site is the region which shows me that 0.0329 will go out of the specification limit, and this side says that 0.0011 will go out of the specification limit. So, typically I would have 0.0329 plus 0.0011 equal to 3.0340, 3.4% as the defective product, reject product. So, if I just convert this into the number, then you can say that 4000 into 4000, that is 40 lakh, into 0.0340 into 2.5 is the cost dollar. So, I would be almost losing $340,000. So, it is not a small amount. So, proportion of product non-conforming, if you just move the process mean towards the value of 90, then again you will have some non-conforming, but this goes down and the proportion of product non-conforming is 0.0142. So, typically it is 0.0071 plus 0.0071, and if you do a little bit resetting, you will get 1.42%. So, if I consider this 1.42%, then total monthly scrap will come down and it would be 1,42,000. So, compared to the previous one, which was $3,40,000, it has come down to the 1,42,000. So, saving would be almost 1,98,000. So, just see the importance of, say, knowing the process capability and doing a little bit setting to my process and setting it at the right mean can really help me to reduce my, say, scrap, and hence there could be huge saving in my say rejected products, scrap products, and this is where it is beneficial. So, you have natural tolerance limit and specification limit. Just again to remind you that natural tolerance limits are pertaining to the process capability and variability of the process, wherein your specification limit are basically given by the customer, and we try to produce the product within this particular specification limits. So, you have couple of other indices, derived indices like upper capability index. So, CPU is basically USL, upper specification limit. I just consider half minus mu divided by 3 sigma because it is half, and the desirable is that CPU should be greater than or equal to 1. Similar way, short term I can find my CPU just by dividing it by sigma st, that is short term, and I can find long term PPU dividing it by sigma lt. So, this is the process capable with respect to upper specification, CPU is greater than 1, and same way you define the lower, and lower is for short term CPL, for long term it would be PPL. So, we can just see the example of CPL, that is with respect to one specification limit, lower specification. So, consider the example on the inside diameter of casing of water meter, the same example, and suppose there is only one lower specification limit of 80 mm. So, now find the CPL index and comment on the process. So, for any product with an inside diameter of casing below 80 mm, it must be scrapped at a cost $2.5 as we had considered previously. And what measures would you like to consider? So, X bar is 89 mm, S is 1.633. From the previous calculation I can consider, and just by putting this, it is represented on a normal distribution, and I can put this values in the CPL expression. So, it comes out to be 1.837. So, you have CPL greater than 1. So, a very small proportion is below LSL, lower limit, lower specification limit, and if you find the ZL, so this comes out to be minus 5.51. So, proportion below your LSL is less than 0.000000372, and your monthly scrap would just be less than $2.79. So, I can say that move process mean further up if feasible. There is absolutely no problem. So far the lower part is concerned, you have the flexibility to move the process up, to adjust the process in order to improve upon your scrap reduction and the cost saving. So, just see that recommended minimum value for process capability indices, when you consider two specification, when you consider one specification, if you are talking about the existing process where the knowledge is available about the process variability, 1.33 for two-sided and for one-sided 1.25 is okay. When you say new process where the process knowledge is less, process is not stable, you may go for 1.5, 1.45, and similar way you can see the safety, strength or critical parameter existing process 1.5, and when there is a concern of safety, strength, critical for new process, we are just putting the criteria a little bit tougher, 1.67 and 1.6. So, these are the recommended. I must have greater than these values in order to accept my process. So, you have CPK index, already I expressed that it takes into account the mean value, your location part, and tries to say that what is the performance of the process even if there is a shift in my process, and also it considers the process variability through sigma. So, if a process is centered perfectly at the mean value, your CP is equal to CPK. So, a process is not capable. Now, I am talking about CPK which is less than 1, and you can see that you are producing proportion non-conforming on this side, and this is where your CPK is less than 1. We can see the CPK example that you have an electric circuit. The capacitance of the component should be between 25 to 40 and a sample of 25 component yields a mean of 30 pf. Standard deviation is 3 pf. Try to find out the CPK and comment on the process. So, this CPK example I can just figure out through calculation that LSL is equal to 25, USL is equal to 40, X bar is equal to 30. My M comes out to be 32.5. So, 0.0475 is the rejection which I can show in the shaded region. So, CPK is my minimum of these two and 0.556. So, CPK is less than 1, the process is unable to produce any conforming product, and typically the corrective action is move process mean towards target value, that is 32.5, and if feasible try to also reduce the process variability. So, you can further extend the calculation to find the proportion non-conforming. So, Z LSS 25 minus 30 divided by 3, this will give you minus 5 divided by 3 minus 1.67. Similar way you can find the Z USL 40 minus 30 by 3, this will give you 3.33. So, USL is the proportion below your USL is comes out to be 0.0475 when you use this Z table and refer the normal table, and USL is 0.0004 which is quite negligible. So, total proportion non-conforming on both the side would be 4.79%. Now, process performance you can improve by shifting the process as I mentioned, and suppose I shift the process, let us say, to the target value 32.5 pf. So, in this case you once again calculate the ZL and ZU and you will get the proportion below LSL is 0.0062, above USL is 0.0062. So, proportion non-conforming would be only 1.24%, and this would really improve your situation. Now, you have another measure, this is CPM. So, typically this measure is aimed to say process capability index of the mean, and that accounts for the process location target value, and it is also called the Taguchi process capability index. So, I am just giving you the expression for your reference, and you can plug in the values for a particular case we just did. For one example, USL minus LSL divided by 2, 3 into square root of sigma square plus mu minus t, t is the target value, square, and this will give you another measure, that is CPM. So, in summary we can say that when process average and target value are equal, CPM equals CPK. When the process average drifts from the target value, CPM is less than CPK, and PPM index is analogous to CPM, only long term and short term difference is there. So, my summary on process capability is that preset product or service dimension tolerance, for example, bottle fill might be 16 ozone plus or minus 0.2, based on how product is to be used, based on the customer expectation, capture this data and find the CP and CPK. CP is the total band USL minus LSL, CPK considers the mean value, and you can further see the three situations, three cases. A, your process variability meets the specifications, and B, process variability outside the specification, and C, the variability is extremely less, process variability within the specification limit. So, we have process variability and specification limit, and we try to capture the health of the process. So, CP and CPK for Six Sigma, CPK should be targeted to 1, it needs attention, and CPK 1.33, it is a desirable, 1.5 excellent, 2 is basically Six Sigma process. So, we are targeting CPK 2 for Six Sigma, 1 or less than 1 not capable, 1 demands immediate attention. Now, to conclude with, we have process performance, and typically you try to capture the process performance of the process which is under statistical control for a long period of time, not by focusing on the subgroup as we did for CP, CPK and other measures. So, PP, PPK, PPM are the measures which basically talks about process performance indices. Same way you can capture, only thing you have to consider the long term process standard deviation, and here you consider the halfway, but again it is long term. So, sample standard deviation, but for a reasonably long period of time. So, PPK determines the proximity of the process average to the nearest specification limit, and this tend to be bit larger than their corresponding process capability indices, since they are often based on small sample sizes as I mentioned. So, just think it, couple of questions for you to introspect. What are the advantages of having a process spread that is less than the specification spread? What should be the value of CP be in this situation? Could CPK be less than 1 here? What conditions must exist prior to calculating the process capability? Discuss how process capability can be estimated through process control charts. And suppose that the question 3, suppose that the dimension of an assembly has to be within certain tolerances. So, please discuss how tolerances could be set for the components given that the difference between two component dimension comprises this assembly dimension. Assume that inherent variability each component is equal. And finally, you compare the various process capability indices CP, CPK and CPM. Please see these references to revise your concepts. And to conclude, process performance indices tend to be a bit larger than their corresponding process capability, since they are often based on smaller sample size. Thank you very much for your patience and interest in learning this particular topic, and we have talked about various issues in the measure phase of my DMAIC cycle. So, keep revising, keep noting down your queries, also refer the suggested texts, and be with me, enjoy.